Welcome. We are going to do section 2-4. This is talking about continuous functions. Almost every theorem in calculus has a prerequisite that f is continuous. And so in order to use those theorems, we need to define what continuous means. And the concept of it is actually really simple. It just means that there aren't any breaks or holes. But to define that formally is important in mathematics. So this is going to be kind of your first step into kind of how proofs work in regular math. Like I know you did those in geometry, but those are quite different. So how do you prove something in calculus? And the way that we do that is using the definition. And the definition usually has some setup and qualifications, and then things that the function has to have in order to meet those meet the requirements. So let's define continuous. F is continuous at a point C if these three things happen. F of A is defined. Sorry, I don't mean A. I mean C. If f of C is defined, C is our point. If the limit as x goes to C of f of x is defined, or we'll say exists. And then lastly, if f of C equals the limit as x goes to C of f of x. So number 3 is just saying, do these two values equal each other? That's what that's saying. And if a function meets all three of those qualifications at a point, then we say it's continuous. So how do you prove something's continuous? You walk through those 3 steps. So I'm going to do it just in the context of a picture first, and then we'll talk about what it looks like to actually algebraically do it. Because I want you to have a really solid concept of what continuous is. This is obviously continuous, and we're going to call this point, we're going to investigate this point right here, C. So let's walk through the definition here. At that point, I'm going to take C, I'm going to go up to the function, I hit the function, and I'm going to go over and find my y value there. And that is my f of C. So this obviously exists. Basically, it's saying, is there a point on the graph right above C or below, as the case may be, okay, on the function? So that's true. It's there. So that means that f of C is defined, okay, or it exists. The next thing that we're going to look at is the limit. The limit says, I want you to go a little to the left of C and go up to the function. Where are you? And a little to the right of C and go to the function. Where are you? And what are you real close to? Well, it looks like you're close to f of C. And if the left, this was our left limit, and our right limit, if they are close to each other, if they are the same, then that means that the limit exists. So we can say this limit exists. And then the third step is, are they the same? Does this equal this? Well, let's look. Here's f of C, and here's the right and left limits coming into the same value. So that means that they are equal. So f of C equals the limit. And because all 3 of these qualifications are met, we can say that f is continuous at that point C. Okay, so that's the idea. Now, I think it's more instructive to look at problems instead of things that work. This is obviously continuous, and you'd probably say, like, well, I think that's obvious. And it is obvious, or maybe I think it's harder to understand sometimes what these parts are saying until you see where they fail. So let's take a look at that. The first situation is a function with a hole. We're going to look at this point right here, C, and we're going to walk through the definition. So first part of the definition, f of c is defined. I walk c up to hit the function. Oh my gosh, look what happens. I never hit the function because there's a hole there. There's no f of c. The function's not defined at that point. So this is an example of f of c is not defined. And so we would say that f is not continuous at C because it fails the first standard of f of c not being defined. Okay, so that's what number one is, making sure that there aren't holes in your graph. That's what's happening. Okay, let's look at number two. I'm going to shift this definition down so we can see it while we're looking at the other two. Okay. Second problematic picture is a graph that is defined but has a break. Okay, so this is your C value. All right, let's go through the definition. Here's step one. F of c is defined. I take c. Can I hit the function? Yes, I can. I hit it right there at that closed hole. This value right here is f of c. So my first qualification is met. F of c is defined. All right, second qualification. The limit. So in order to evaluate the limit, I want to start a little to the left of c. Go up. Where am I? I'm right here. This is my left limit. And I want to look a little to the right of C. Now look what happens. I bypass that piece of the graph. I have to go up to this top piece. This is the right-hand limit. And we talked about in section 2 that if the right and left-hand limit don't match, then that means the limit doesn't exist. So this is an example of a graph that fails the second qualification. Okay, does not exist. So we would say f is not continuous at C. Okay, and obviously you can see it's got a break in it. It's not continuous. All right, so that's the second step. And so the second one is eliminating breaks in the graph. The first one eliminates holes. The second one eliminates breaks. Third, what's the third step do? Okay, here's your function. Here's C. Let's check this guy out. Go through the steps with me. 1, f of c. Okay, that is defined. There is actually a dot at C. This is f of c. Okay, so f of c is defined. Second step, limit. Little to the left of C. Okay, little to the left of C, I'm right here. This is my left-hand limit. And a little to the right of C, I'm right here. So basically same place because I can get close as I want. So that means the right and the left-hand limit are equal. And so that means the limit does exist. This does exist. Okay, so that leaves us the third step in the definition. Are these two equal? Does the first one equal the second one? Well, let's look. This is the first one. That's f of c. That's this value. And this one's the second one. That's the limit. They are not equal. So what the third step is eliminating is a hole that got shifted somewhere. Okay, so we would say that f of c does not equal the limit as x goes to c of f of x. And so f is not continuous at c. So all three of these graphs that we looked at are not continuous, but they fail in three different ways. Okay? And so some of your homework will ask you to look at different graphs and say, where does this fail? Why does this fail to be continuous? And what they're looking for is which part of the definition doesn't work here, basically. Okay? Now, there's three types of, what we call these things are discontinuities. Okay, so it's continuous or it's discontinuous. There are three kinds of discontinuities. One is called a removable. This is just vocab. Okay, discontinuity. Throw these on a note card and just go over them at breakfast for the next 5 days. You'll have them memorized. A removable is a hole. Okay, so this is a removable discontinuity. A jump discontinuity is a break, like this, okay? And an infinite discontinuity is an asymptote. So that would be like, this graph right here is discontinuous at this asymptote because it's going up to infinity. That's why it's called an infinite discontinuity. Okay. All right, so let's do some examples with actual functions. Again, my rule of thumb, you get any piecewise function, any absolute values, anything looking weird, it will benefit you to draw a picture. Okay, so what I have here is I have an x squared function. Okay, that looks like this. And that's going to be everywhere except 1. So that means that there's going to be a hole right here at 1. And at 1, I want it to be 3. So that means that I've got a point right up here at 3. So that's my function. Okay. And the question is f continuous at 1? Why or why not? So here's the strategy. If you say yes, then you have to show me how it succeeds in the 3 parts of the definition. If you say no, you have to cite which one fails. Okay, that's the strategy for proofs on these. And you can just kind of talk through them, or you might have to write some English on some of these, okay? So I'm going to look at this graph and I'm going to say it's definitely not continuous, right? If I was a roller coaster, I'd be worried about that hole coming up. The discontinuous functions have breaks in the roller coaster tracks. So the question is, which one of the definition pieces fails? So let's pull the definition down here again. You cannot do these problems without looking at a definition. And let's check them. Okay. The first thing I'm going to check is it defined at 1? 1 is our C. That's the place that we're interested in. Well, I can go up and I can actually hit a point on this function. So this checks off. Does the limit exist? Well, a little to the left of 1 and a little to the right of the 1 is the same place. So yes, this limit exists. Are they the same? Is f of c equal to the limit? And the answer is no. So I would write for my answer, I would say f is not continuous since f of c equals 3 and the limit as x goes to, sorry, not f of c, that's too general, f of 1, because 1 is our c value, and the limit as x goes to 1 is 1. So 1 does not equal 3. Okay, and that proves it. That's all you need to do. So several homework questions where it's asking where does this fail, and you can navigate through those. You can either graph them or you can just calculate the limits. All right, so now what does it mean for the whole function to be continuous? F is continuous on an open interval if f is continuous at every point. So basically, yeah, I gotta go point by point. Now, nobody's gonna really do that, so there's a little bit of waving of our hands in this section. But I like how your homework goes about this. They actually ask you to define where they are continuous. So it's going to say something like, state the intervals for which this function is continuous. Okay, so basically, again, we're saying where are there breaks? Okay, breaks or holes, breaks and holes are problems in the domain. So we talked a lot about this in pre-calculus. Domain, you have a couple issues. Your first issue is fractions. Fractions for domain, the denominator can't equal 0. That's a break in the domain. The second is roots. Roots, we're talking even roots. Roots can't have to be greater than or equal 0. You can't root a negative. This is a no-no. Okay, that's a break in the domain. The third is logarithms. When we did those, you can't log a negative also, and that's a no-no. That's a break in the domain. There's also some domain issues with trig functions, and I'm not going to go into those here. If you need some help with those, let me know, but we talked about what those look like and like how secant, cosecant, and tangent and cotangent have asymptotes. Those are also breaks in the domain. So if I want to know where is this function continuous, what I'm looking for is where does it go wrong. Okay, so this is a rational function, and it's got a vertical asymptote at 3 right here, and it's got a horizontal asymptote at 1. If you need to use a graphing calculator, you can. We did learn how to graph these in pre-calc. So x-intercept of -2, y-intercept down here. This guy's going to look like this. Okay. So the question is, where's the domain? Well, this thing is defined on the x-axis for all of these values up until here. This is the break. And then it's defined for all these values out onto infinity. So where is it continuous? It's continuous in this section and then also in this section. So the way we write that in interval notation is -infinity to 3 and union with 3 to infinity. and these are the intervals for which f is continuous. So basically you're graphing it or doing some algebra to figure out where are the problems, and then everywhere else is your answer. Okay, eliminate the problems, and the rest is your, the rest of the domain is where f is continuous. Okay, let me show you one other type of problem you'll see on your homework. I think this homework set is a real, you really need to think on this homework set. It's not drill and practice as much as do you really understand what this concept means, what a limit is, and what it's saying. So spend some time on it. It's a really good homework assignment, and I think if you spend some time really reading it carefully and thinking, you'll get a lot out of it. So the last type of thing you'll see on there is they'll give you a function. Typically these are piecewise functions, and they're going to give you a variable here over in the parameter, or in the breakouts. We're using a, whereas usually there would be like a 2 or a 3 there. And it says find the values of, or value of a that makes f continuous. Okay, so let's draw a picture and see what they're saying here. All right, so I've got, oops, I didn't draw my axis well enough because I need a negative down here. Okay, so what I've got is, first I'm going to draw this. This is a parabola, and it's shifted down 3. So I'm going to draw these dotted just so we can erase part of them. So that's the parabola, okay? And then I've got a line, y-intercept of -7 right here, and a slope of 4. So up 4 over 1, 4 over 1, 4 over 1. Okay, so it looks like this. Pretend that it's straight. I know it's, okay. So that's your, oh, I didn't do it dotted. Oops. Let's do this over the top. And okay, so those are my two graphs, the parabola and the line. The question is, where should I break this? Where should I transfer from the red graph to the blue graph so that it's continuous? Okay, so for example, what if a was 0? If a was 0 and I was going to cut this right here, that means that it would be the blue graph on the right and the red graph on the left. So that would make it be this on the left right here. Whoops, sorry. This on the left, and then this on the right. Now look at that graph. That black graph is not continuous because there's a big giant break right there. So 0 wouldn't work. Okay? That's what it's asking, is where can I break this so that I don't have a big gap. Now the answer is you want to break it where they touch each other, because if they're touching, then there won't be a break. Okay? And that understanding is the key to how to algebraically solve this problem. And what you're going to do is you're going to take this function, x squared minus 3, and you're going to set it equal to this one, because you want to know where are these equal and where do they touch, because that's where I want to break it so that my transition from the left to the right is seamless and there's no holes. Okay, well, how do we solve this? Get everything on one side. We're going to add over the 7. So I get 4 set equal to 0. It's a quadratic. I factor. So x equals 2. Now I drew a pretty decent picture, and if you saw it, you could tell that they were touching at 2 right here. Okay, this is x equals 2. And so that, that might happen, but I want to see this algebra I want you to lay it out. So set those two equal and solve. So my answer would be that x should be, or a should be 2 in order to make these continuous. And then what you'll have, let me draw it in, let me do highlighter so you can see. So if I take this parabola all the way over to x equals 2 and then transition to the blue line, then I have a seamless transition right there, and the whole function's continuous. Okay, so that is how you do those. And one more theorem for this section. Okay. This is called the intermediate value theorem. This is a very important theorem. It's really useful. If f is continuous, there's that qualification that f is continuous, which happens so often, on an interval, a closed interval, a to b. And if L, we'll say capital L, is a real number between f of A and f of B, then there is a number C in the interval AB such that f of C equals L. Okay. Let me draw a picture. I always draw pictures for theorems. The pictures help so much for me, because this just feels like garbage. You're like, what in the world is happening right there? Okay, so here's a function. Let's draw like this. Okay, it's continuous, and we're going to look at it from A to B over here. Okay, L is a real number between f of A and f of B. So let's look. Here's f of A, and here's f of B. And L is some real number between those. And it can be any number. Let's just say this here. It can be anywhere. We're going to call that L. What the theorem says is that if this black function is continuous, and you pick a number here between these two, then there is some number that correlates to that on the x-axis. We'll call it C. And C is between A and B. So this says that L is a real number between f of A and B, then there is a C such that that maps onto L. And that makes sense to me. It's like, okay, here's the top and here's the bottom. If you pick something in the middle, it's going to map onto something in the middle. That's what it's saying, which might not feel revolutionary, but there's some pretty powerful things that you can do with this. So let me show you one that you're going to see in your homework. It'll say, use the intermediate value theorem, IVT is our abbreviation for that, to show that f of x equals x minus 2 has at least 1, 0, or x-intercept, that's what a 0 is, on the interval from 0 to 3. Now, here's how, in real math land, here's how you use the theorem, okay? You take the theorem, and you have to first verify the if parts, okay? So, if f is continuous, well, so we go down here, and the first thing that I need to say is, one is, note, f is continuous. Now, there's a couple things that we take for granted. This is a polynomial. It's a parabola. Everybody at this stage in the game knows that a parabola is continuous. So if you just get a polynomial like that, then you just say, hey, it's continuous. Duh. Okay, but if you get a rational function or something, you probably have to mention that, hey, there's an asymptote, but it's not in this interval. Like, you're going to need to kind of write a sentence. Don't be afraid to write in English and say, hey, this is f is continuous, okay? Now, also, we want to know that L is a real number between f of a and f of b. So the first thing that we need to know is, what is f of a and b? Okay, a and b are the parameters of your intervals. So in our case, that's going to be 0 and 3. So the next thing we need to do is find what is f of 0 and what is f of 3. Okay, so I'm going to plug in those values. F of 0 is -2. And f of 3 is 7. Okay, now we want to show that there's at least one 0. So let's draw a picture. Just so you understand how we're applying the theorem. First of all, f of 0 is -2. So 0, -2 is on the graph. And then f of 3, 6, 7 is 7. So the coordinate, this is the coordinate 3, 7, and this is the coordinate 0, -2. Okay, and if you know what this looks like, this is a parabola and it's shifted down 2. So it looks like this. Okay, and it goes up over here, but we're only looking from the interval from 0 to 3 here. And I want to show that there's at least one x-intercept. Well, what do we know about an x-intercept? An x-intercept, here it is by the way, has a y value of 0. Do you see that? Okay, so look up at the top here. What we're saying is our L value is 0. That's right here. That's going to be our L value that we're going to pick. And L is definitely between 7 and -2. How do I know that? Because -2 is negative, 7 is positive, so I for sure have a 0 value in between 7 and -2. Okay, so this is the application, is finding these zeros. So what I say is, my third step is I'm going to say, notice that L is between, or sorry, not L, L equals, sorry, I'm going to call it 0. L equals 0 is between -2 and 7. So what I've done is I have shown the two qualifications for the intermediate value theorem. I've shown that f is continuous, and I've shown that there's a real number between the endpoints 0. Okay? And then it says then. So now I can make the conclusion. I can write the conclusion out because I've met the requirements here. I can say, so, and the way we write this is, therefore, by the intermediate value theorem, there exists a C in the interval 0, 3. It's right here. This is our C value that we found between 0 and 3, such that, oops, spelling, that f of C equals 0, my L value. Okay, and that shows you that there's a root. Now, these can be a little tricky. I recognize that I may have lost a few people. That's okay. We can do some problems like this. There's some on your homework. We can do them in class to kind of, because proofs are new, you know, and we've never done those before, so that's okay. And you'll start to see that they all kind of look the same once you get the language down. But before I end here, I do want to tell you some shorthand. If you're interested, you do not have to use this, but if you're going on in math, you might want to throw this in your brain because people use it. First is therefore is 3 dots like this. That stands for therefore. Okay? This phrase, there exists, we use all the time, and what it looks like is this. That's the shorthand for there exists. It's a backwards E, but it's squared off. It's not round. Okay? And this whole in the interval is actually a round forward E. Okay? And then such that shows up all the time in these conclusion statements. We always put just ST. So if I was going to write this in the shorthand, I would write, therefore, by the intermediate value theorem, there exists a C in this interval such that f of C equals 0. So if you're interested in that, you can use that. That's fine. If you don't like that and that's too much, you do not have to. Just want to show you that. So go ahead and try some of the homework, and I will see you in class.